On the left, an electrical circuit, currents flowing in and out of every junction, perfectly balanced. On the right, a graph, nodes, edges, regions. Circuit analysis and the graph topology seem unrelated, but one matrix connects them, the incidence matrix. It links Kirchhoff's current law to Euler's famous formula. The bridge between them is the null space. Here's the punchline. For any connected graph, nodes minus edges plus loops equals 1. 4 minus 5 plus 2 equals 1. By the end of this video, you'll understand why that equation must be true, not from counting, but from linear algebra. Let's make it concrete. Here are 4 nodes, labeled 1 through 4. We now connect them with 5 directed edges, appearing one at a time. Edge 1 goes from node 1 to node 2. Edge 2 goes from node 2 to node 3. Edge 3 goes from node 1 to node 3, cutting across the diagonal. Edge 4 goes from node 1 to node 4 along the left side. And edge 5 goes from node 3 to node 4 along the bottom. The edge directions are chosen by convention. Any consistent assignment works. And this gives us a connected graph. 4 nodes, 5 edges. Every node can reach every other node through the underlying connections. Now we encode this graph as the incidence matrix A, 1 row per edge, 1 column per node. Here is the rule. Place -1 at the start node of the edge and +1 at the end node. All other entries in that row are 0. Let's build it row by row. Edge 1 goes from node 1 to node 2, so we get -1, 1, 0, 0. Edge 2 goes from node 2 to node 3, giving us 0, -1, 1, 0. Edge 3 goes from node 1 to node 3, -1, 0, 1, 0. Edge 4 goes from node 1 to node 4, -1, 0, 0, 1. And edge 5 goes from node 3 to node 4, 0, 0, -1, 1. That gives us our 5 by 4 incidence matrix A. Notice that every row sums to 0. And that's because each edge takes from one node and gives to another. -1 plus 1 is always 0. Look at the graph. Edges 1, 2, and 3 form a triangle. Edge 1 goes from node 1 to node 2. Edge 2 goes from node 2 to node 3, and edge 3 goes from node 1 to node 3. That's a closed loop. Here's the key insight. Take row 1 of A, -1, 1, 0, 0. Now add row 2, 0, -1, 1, 0. Let's do the addition element by element. In the first column, -1 plus 0 gives -1. In the second column, 1 plus -1 gives 0. In the third column, 0 plus 1 gives 1. In the fourth column, 0 plus 0 gives 0. The result is -1, 0, 1, 0. And that is exactly row 3. So row 1 plus row 2 equals row 3. The loop in the graph predicted this dependency before we even touch the algebra. Edge 1 goes from node 1 to node 2. Edge 2 goes from node 2 to node 3. That composite trip from node 1 to node 3 matches edge 3, which goes directly from node 1 to node 3. Every closed loop in the graph creates a linear dependence among the rows of A. Our matrix has 5 rows and 4 columns. For a connected graph with n nodes, the rank, the number of independent rows, equals n minus 1. With n equals 4, the rank R equals 3. That means 2 rows depend on others, and those correspond to 2 independent loops in the graph. To find the independent rows of the incidence matrix, we identify a spanning tree, a connected subgraph that touches all nodes with no loops. Edges 1, 2, and 4 form such a tree. Notice how the tree reaches all 4 nodes while containing no cycles. A spanning tree on n nodes always has exactly n minus 1 edges. Here, 4 minus 1 equals 3. These 3 tree edges correspond to the 3 pivot rows of A, rows 1, 2, and 4. The remaining edges each create a loop when added back to the tree. Adding edge 3 completes the triangle, creating loop 1. Adding edge 5 creates loop 2. This gives us exactly the two independent loops we predicted earlier. We've seen what A tells us about the graph. Now let's transpose it. A transpose is a 4x5 matrix. Each row corresponds to a node. Let Y be the vector of edge currents, Y1 through Y5. The equation A transpose times Y equals 0 expresses a fundamental physical law. Row 1 of A transpose is -1, 0, -1, -1, 0. This gives the equation -y1 minus y3 minus y4 equals 0. On the graph, edges 1, 3, and 4 all leave node 1. The equation says the algebraic sum of currents at node 1 vanishes. Current in equals current out. This is Kirchhoff's current law, often called KCL. Now check row 4 of A transpose. It reads 0, 0, 0, 1, 1. This gives y4 plus y5 equals 0. Edges 4 and 5 both connect to node 4, and their currents must balance exactly as KCL demands. Conservation holds at every node, and it wasn't assumed. It follows directly from the matrix structure. The null space of A transpose, the set of all current vectors, Y, where A transpose times Y equals 0, describes every possible current pattern that satisfies Kirchhoff's current law at all nodes simultaneously. The null space of A transpose has dimension m minus r, which is 5 minus 3 equaling 2. This means exactly two independent current patterns satisfy Kirchhoff's current law. The first basis vector is 1, 1, -1, 0, 0. This represents 1 amp flowing along edge 1 from node 1 to node 2, 1 amp along edge 2 from node 2 to node 3, and 1 amp backward on edge 3. The -1 means the current opposes edge 3's assigned direction, flowing from node 3 back to node 1. So this current circulates around the triangle formed by nodes 1, 2, and 3. The second basis vector is 0, 0, 1, -1, 1. This represents 1 amp along edge 3, 1 amp along edge 5 from node 3 to node 4, and 1 amp backward on edge 4, flowing from node 4 back to node 1. This current circulates through nodes 1, 3, and 4. Now consider the outer boundary of the graph, which follows edges 1, 2, 5, and 4. Its current vector is 1, 1, 0, -1, 1. Is this an independent loop? Let's check. Add the two basis vectors component by component. 1 plus 0 gives 1, 1 plus 0 gives 1, -1 plus 1 gives 0, 0 plus -1 gives -1, and 0 plus 1 gives 1. The result is 1, 1, 0, -1, 1, which is exactly the outer loop vector. So the outer loop is the sum of the two basis vectors. It is a valid current loop satisfying KCL, but it is not independent of the first two. Only m minus n plus 1 loops are independent. Here that is 5 minus 4 plus 1, which equals 2, exactly two independent loops. We found ranks, null spaces, loops, and trees. Now the dimensions all come together. A is m by n, 5 rows and 4 columns. For a connected graph, the rank R equals n minus 1. Here that's 3. The left null space of A transpose has dimension m minus r, which is 5 minus 3 equals 2. Those are the independent loops. Let's express the number of loops algebraically. Loops equals m minus the quantity m minus 1, which simplifies to m minus n plus 1. Rearranging, we get n minus n plus loops equals 1. Now plug in our numbers. 4 minus 5 plus 2 equals 1. This is Euler's formula for connected graphs, and it's not specific to this example. Let's prove it algebraically. Expand n minus m plus the quantity m minus n plus 1. The n's cancel, the m's cancel, and we're left with just 1. Rank-nullity guarantees this identity for every connected graph. Now here's the complete picture of all 4 fundamental subspaces. The column space of A has dimension 3. These represent independent null potentials. The null space of A has dimension 1. That's the constant potential, the ground. The row space of A transpose has dimension 3. These correspond to 3 edges. And the left null space of A transpose has dimension 2, the independent loops, right? Every dimension traces back to the rank, and Euler's formula is simply the dimensional bookkeeping. Now let's step back for the full picture. Nodes are zero-dimensional objects, just points. Edges are one-dimensional, they have lengths, and loops enclose two-dimensional regions, they have area. Euler's formula says nodes minus edges plus regions equals 1. For our graph, that's 4 minus 5 plus 2, which equals 1. This is a topological invariant, and it holds for every connected planar graph, and linear algebra proves this through the rank-nullity theorem. It's pure dimension counting. The incidence matrix A bridges algebra and topology. Its null spaces encode physical conservation laws like Kirchhoff's current law. Its dimensions encode geometric truths like Euler's formula. From one 5x4 matrix, we get 3 powerful ideas. First, row dependencies reveal loops. Second, null spaces enforce conservation. And third, dimension counting yields topology.